Our topic is algebraic expressions and sets of numbers. The first objective in this topic is identify and evaluate algebraic expressions. So we've got some terminology that we need to get down first. First, a variable is a letter used to represent any number. So X could be a variable, Y could be a variable, Z could be a variable, S can be a variable, T can be a variable, and these variables represent any number. So sometimes X is 2, but sometimes X is 7, for instance. Now, on the other hand, we have a constant, which is either a fixed number or a letter that represents a fixed number. So 3 is a constant. 42 is a constant. 54 is a constant. 0 is a constant. Or if we say X equals 2, where X is always 2 and nothing else, that's a constant. That's a letter that represents a fixed number. Or pi. Pi is a Greek letter that represents a fixed number, 3.141592653589799, on and on, forever, never repeating and never terminating. So variable versus constant. Variable can be anything. Constant is a very specific thing. And it got kind of blurry when I gave the example X equals 2 because X is a variable equals 2. That makes it a constant. An algebraic expression is formed by numbers and variables connected by the operation of addition, subtraction, multiplication, division, raising to powers, and or taking roots. So some examples of algebraic expressions. 3x plus 5. We're joining the constant 3 with the variable x by multiplication, and then we're joining that to the constant 5 with addition. 5a squared minus 6a plus 40. The a has been raised to the second power. The a to the second power is joined to the 5 with multiplication. We're then joining with subtraction 6 times a, and then we're adding the constant 40. Y to the fourth minus y squared plus 15 all over 4y. On top, we have an algebraic expression. On the bottom, we have an algebraic expression. And the fractional notation, the rational notation, just means divide. Take the top, divide by the bottom. So anytime we join numbers and variables and we add them, subtract them, multiply them, divide them, raise them to powers, or take roots, we're making algebraic expressions. And right now, these algebraic expressions contain variables. If we were to evaluate an algebraic expression, we'd be substituting a numerical value for each variable into the expression and simplifying the results. So we're given values for X, values for Y, values for Z, values for S, values for T. And we substitute them in and then do the operations. So an example, the area of a rectangle with length L and width W is L times W. Find the area of a rectangle with length 5 meters and width 3.2 meters. So length is L. When we have a length of 5, we're saying 5 is L. So substitute 5 in for L. Width is W. So width 3.2 means W is 3.2. Substitute 3.2 in for W. So replace L with 5, W with 3.2 in the algebraic expression L times W. So L times W becomes 5 times 3.2. And 5 times 3.2 gives us 16. Meters times meters is square meters. Now that was a wordy example, literally a word problem. Here's a more straightforward example. Evaluate b minus 5a when a is 4 and b is 35. We do the same things. We replace a with 4. We replace b with 35. So b minus 5a, or 5 times a, becomes 35 minus 5 times 4. And now start to simplify. 5 times 4, that's 20. 35 minus 20 is 15. We're careful to follow something called the order of operations that we'll look at a little bit later. You should know the order of operations already from previous classes, though. Multiplication comes before subtraction. That's why this wasn't 35 minus 5 equals 30, and 30 times 4 is 120. The answer changes depending on the order you do the operations, which is why we have an order of operations. The second objective in this topic is identify natural numbers, whole numbers, integers, rational numbers, and irrational real numbers. So we have to start by talking about the number line. And a number line is a line on which each point is associated with a number. There is a number line. There is negative 4.8. There is positive 1.5. We're separated into the negative and the positive numbers. Negative on the left, positive on the right. The left and right of what? The left and right of 0. Now here we're showing 0 in the middle, but 0 doesn't have to be in the middle of a number line. We can draw any portion of the number line and it's still the number line because of the fact that it goes on forever. And it should be in both directions. This is more a visualization of a number array. But you can imagine there's an arrow on the left side as well, going negative and negative and negative forever. And on this line, we have numbers, and even the numbers we don't see are on here. Negative 4.8 was between negative 5 and negative 4, closer to negative 5 than negative 4. And that's just a point on the line. Another point in the line is 1.5, halfway between 1 and 2. 17. 17's not between negative 5 and 5, but it's part of this going on and on and on forever. So even though we don't see it, it's there. The number line goes from negative infinity on the left to positive infinity on the right. Now, infinity and negative infinity aren't numbers. This isn't like the playground where you're playing some sort of game with your friends and someone says blah, 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 infinity. And then someone else says blah, 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 infinity plus 1. There is no such thing as infinity plus 1. Infinity is not a number that 1 can be added to. Infinity is the idea of on and on forever in the positive direction. Likewise, negative infinity is the idea of on and on forever in the negative direction. But we started talking about infinity and negative infinity and what is a number, what's not a number. Let's start classifying numbers. And the first set of numbers we're going to look at are the natural numbers. These are also called the counting numbers. One nice way of remembering what the natural numbers or the counting numbers are, there's a very famous puppet. You may even say Muppet, and his name is Count. Uh, count counts. One, ha, ha, ha. Two, ha, ha, ha. Have you ever heard count go zero, ha, ha, ha? Nope. So the natural numbers, the counting numbers, they're the numbers that we count with. 1, 2, 3, 4, 5. Not the numbers your parents use when you're about to get in trouble, or maybe not get in trouble, which is why they're using the numbers. 2.5, 2 3/4. Those are those are part of a different set of numbers. But they are not a part of the whole numbers. The whole numbers are just our counting numbers, our natural numbers, with 0 attached at the beginning. So the whole numbers go 0, 1, 2, 3, 4. If we take the negative versions of the natural numbers and we have them going to the left forever, we get the set of integers. The integers are our positive counting numbers, 0, and the negative version of the counting numbers in the order that they appear on the number line. So -16 is an integer. 5 is an integer. 0 is an integer. 0 is also a whole number. 0 is not a natural number. None of the negative numbers are whole numbers or natural numbers. And we have these dots indicating going on forever in one direction or another or both. A bit of vocabulary. That dot symbol is called an ellipsis. And an ellipsis just means to continue in the same pattern. So within these sets, we had objects. The objects were numbers in this case, but we call the objects of a set the set's members or the set's elements. And finally, when we list or attempt to list with an ellipsis the elements of a set, we say that the set is written in roster form. So the roster form of the integers was ellipsis -3, comma -2, comma -1, comma 0, comma 1, comma 2, comma 3, comma ellipsis. That was an attempt to list all of the elements of a set. So it was roster form. Now, a set can also be written in something called set builder notation. This notation describes the members of a set, but does not list them. For example, we would read this as the set of all x such that x is an even natural number less than 10. What? Let's break that down again. So this is a set. We have the braces, so it's a set. And the first thing listed in set builder notation is what qualifies as a member. And what qualifies as a member is an x. What is an x? So this vertical bar means such that x is an even natural number less than 10. So natural numbers are our counting numbers. That starts with 1, 1, 2, 3, 4, 5. But we want the even ones. So 2, 4, 6, 8, 10. Oh, but less than 10. So 10's not included. 2, 4, 6, 8. So roster form would be the set 2, 4, 6, 8. It actually is an attempt to list all the members. Set builder notation is just a description of the members of the set. So again, the set of all X such that X is an even natural number less than 10. So let's do some examples. Let's have some set builder notation given. And in turn, let's write the set in roster form. So A, the set of all X such that X is a whole number between 1 and 8. Well, between 1 and 8, when we hear something like that, give me a number between 1 and 10. 1 and 10 are options. Here, 1 and 8 are options. Whole numbers are just the counting numbers plus 0. 0 is not between 1 and 8, so we have the counting numbers. The counting numbers between 1 and 8 would be a whole number between 1 and 8. 0 would be included if it said between 0 and 8, but it doesn't. So what are the counting numbers between 1 and 8? 1, 2, 3, 4, 5, 6, 7, 8. B, the set of all X such that X is a natural number greater than 100. Well, again, natural numbers, this time 0 would not be an option either way, but it's definitely not an option since we want greater than 100. Greater than 100 does not include 100. So X is a natural number greater than 100. The first option would be 101, and then 102, and then 103, and then 104, and then 105. Somebody stop me. That set is going to go on and on forever. How do we indicate that? We indicate that with an ellipsis. So the roster form here would be 101, 102, 103, ellipsis. In our next set of examples, we're going to determine whether each statement is true or false. And we have this new notation, this weird looking E in part A, and that weird looking E, but with a slash through it in part B. So even if we didn't know what it means, it's doing something in part A and it's not doing something in part B. The thing it is or is not doing is belonging. That weird looking E means is an element of, and when it's crossed out, it means is not an element of. So A says 0 is an element of X, where X is a natural number. Is 0 part of a set where it would be a natural number? No. You didn't see that. That was a mistake. I fixed it. False, since 0 is not a natural number. You may have seen it flash on the screen that 3 is not a natural number. Not only was that a typo, it made no sense as a statement because 3 is a natural number. 3, however, had nothing to do with the problem. The problem was about 0. 0 is not a natural number, so 0 is not an element of that set. That is false. Okay, part B. Part B says 9 is not an element of 4, 6, 8, 10. Well, 9 is not an element of 4, 6, 8, 10. That's true. The only things that would be elements of that set are 4, 6, 8, or 10. The next group of numbers we're going to talk about are real numbers. Real numbers are the set of all rational and irrational numbers combined. In other words, if it can exist on the number line, if you can visualize it on the number line, it's a real number. The set of all x such that x corresponds to a point on the number line. Now, I've used some terms here, rational and irrational numbers. What does that mean? Well, when we see rational, the word rational has the word ratio in it. And when we think of a ratio, we should be thinking of something in fraction form. Rational numbers are the set of all numbers that can be expressed as a quotient of integers with denominator not equal to 0. In other words, fractions. Fractions where we don't divide by 0 because we can't divide by 0. The set of all a over b such that a and b are integers and b is not 0. So that's saying that the top is an integer, the bottom is an integer, the numerator, the denominator. On the other hand, an irrational number is the set of all numbers that cannot be expressed as a quotient of integers. And the set builder notation there would be the set of all x such that x is a real number and x is not a rational number. So that makes sense. You're either rational or you're irrational. You can either be expressed as a fraction or you cannot be expressed as a fraction. How do we know if a decimal can be expressed as a fraction? Well, if it doesn't repeat, and it can repeat digits, like pi has 3.14159. That was a 1 twice, but we're not saying that that's repeating because we had more than 1. Repeating is like 4.513513513513. On and on and on forever. So if it does that, it can be expressed as a fraction. It's rational. If it terminates at some point, 3.125. If it terminates, it can be written as a fraction. It's rational. So if it's non-terminating and non-repeating, it is irrational. Let's look at some examples. Determine whether each statement is true or false. A, 0 is a real number. Well, a real number can be expressed on the number line. Is 0 on the number line? Sure is. True. B, every integer is a rational number. Well, what are the integers? -3, -2, -1, 0, 1, 2, 3. Can we write those as fractions? Absolutely. Anything over 1 is equal to itself. So anything can be written as itself over 1. Therefore, every integer is a rational number because every integer can be written as a fraction. C, square root of 3 is a rational number. So this goes back to what I was saying about the decimals. Do they terminate? Do they repeat? Or do they go on and on forever without repeating? Well, when it comes to radicals, when it comes to square roots, unless it is a perfect square, unless it's like the square root of 9, which is 3, or the square root of 16, which is 4, or the square root of 25, which is 5. Those are the only ones that terminate. Those are the only ones that are rational. The other ones are always irrational. So the square root of 3, 3 is not a perfect square. 3 is irrational. Therefore, it is false. It is not a rational number. It is an irrational number. So just to kind of recap our different types of numbers, we started with the natural numbers, the counting numbers. We added in 0, and that gave us the whole numbers. The whole numbers were positive integers. So when we added in the negative whole numbers, we got the whole set of integers. Then we added in things that can be written as fractions, and that gave us the rational numbers. And then we had this whole other separate category of irrational numbers, things that couldn't be written as a fraction, our non-terminating, non-repeating decimals. All of this taken together is the set of real numbers. Real numbers anything on the number line. The number line itself, which goes in both directions forever and ever, is a real number. I should say anything. I should say the number line represents all the real numbers. Anything on the number line is real. So I'm going to give a set of numbers now. -2, 0, 1/4, -1.5, 112, -3, 11, square root of 2. And we're going to go ahead and list the natural numbers the whole numbers, the integers, the rationals, the irrationals, and the real. So the natural numbers are our counting numbers. As we go through our set, the first one we come to that is a counting number is 112. We also have 11. What's the difference between natural and whole numbers? Well, if we add 0 to the natural numbers, we get the whole numbers. And there is 0 in our set. So 0 is a whole number. And then our natural numbers, 112 and 11. If we take the negatives of the whole numbers and add those in, we get our integers. -2. We already had 0. We already had 112. -3. -3 is an integer. We already had 11. All integers, remember, are also rational numbers. We can just write it as, for example, 11 over 1. And we've written 11 as a fraction, which means it's a rational number. So our rational numbers, -2 still, 0 still. New entry, 1/4. -1.5 can be written as a fraction because it is a terminating decimal. So it is rational. 112. -3. 11. And just because we see the square root sign doesn't mean it's not rational. We have to look underneath the square root and see, are we taking the square root of a perfect square? Are we taking the square root of 1, 4, 9, 16, 25, so on and so forth? We are not. 2 is not a perfect square, which means it is not rational. It is irrational. It was the only number left. Everything else was a rational number. And all of them are real numbers. We take the rationals and the irrationals together. Let's do another example. If you want, you can pause this one and try it. Natural numbers. At first glance, you might be looking through this and you might say there are no natural numbers, but you would be wrong. Because what we see here as the square root of 25 is actually the number 5. So the square root of 25 is a natural number. To get our whole numbers, we would add 0 in, but 0 is not a member of this set. So the square root of 25 is still the only whole number. Since it's a whole number, it's also an integer. Do we have any more integers? We do. Negative 15. That's it. Rational, things that can be written as a fraction. That includes all our integers. So the square root of 25 is rational. Seven thirds. Negative 15. Negative 3/4. Square root of 5, that's the square root of a non-perfect square. That's irrational. Negative 3.7, that's a terminating decimal. That is rational. And 2 over 0. It looks like a fraction, but the number one rule of math is that you can never divide by 0. You cannot have 0 on the bottom of a fraction. And therefore, 2 over 0 doesn't exist. It can't be any of these things. It's not irrational. It just doesn't exist. The only irrational number we had was the square root of 5. So our real numbers are the square root of 25, 7 thirds, negative 15, negative 3/4, square root of 5, and negative 3.7. Take our rationals and our irrationals together. We couldn't say all this time because 2 over 0 is not a real number. It does not exist because 0 on the bottom of the fraction dividing by 0. Undefined. Does not exist. The third objective in this topic is find the absolute value of a real number. So let's talk about absolute value. The absolute value of a real number A, denoted by the absolute value of A, is the distance between A and 0 on the number line. So the absolute value of -4 is 4 because -4 has a distance of 4 from 0. Literally count from 0 to -4. 1, 2, 3, 4. Meanwhile, the absolute value of 5 is 5 because 5 is 5 from 0. Start at 0. 1, 2, 3, 4, 5. In practice, you can think of the absolute value as the make positive function or the make positive rule. We see -4 inside the absolute value symbols. What do? We make it positive, 4. We see a 5 inside the absolute value symbols. What do? We make it positive, 5. So let's find the absolute value of each number. What is the absolute value of 7? Well, make positive, 7. What is the absolute value of -6? Make positive, 6. What is the absolute value of -4/5? Make positive, 4/5. And this doesn't really apply here. What is the absolute value of 0? We can't say make positive. There's no such thing as positive 0. 0 is in between the positives and the negatives. So we go back to the definition. What is the distance from zero of zero? Well, it's already there. It's a distance of zero. The absolute value of zero is zero. Now, related, but not at all the same, and not even the opposite, objective 4 of this topic is find the opposite of a number. So opposites, also called additive inverses, are two numbers that are the same distance from zero but lie on opposite sides of zero. So picture the number line. The opposite of a number A would be the number negative A. 3 and negative 3. 7 and negative 7. Both the same distance from zero, just in opposite directions. And it shouldn't be too much of a stretch to get you to believe that the opposite of a positive 4 is a negative 4, and that the opposite of a negative 5 is a positive 5. From there, we can use the double negative property. For every real number A, the opposite of A is A. What? Well, take the number 6. The opposite of 6 is negative 6. What's the opposite of negative 6? Positive 6. The opposite of a negative number is a positive number. Two negatives make a positive. So what's the opposite of negative 35? Positive 35. What's the opposite of positive 12? Negative 12. What's the opposite of negative 3/11? Positive 3/11. What's the opposite of positive 1.9? Negative 1.9. The fifth objective in this topic is write phrases as algebraic expressions. When we translate phrases in math, there are some key words that when we see them, we know they mean specific things. They tell us, hey, see this word, we add. See this word, we subtract. See this word, we multiply. See this word, we divide. So the addition keywords are sum, plus, added to, more than, increased by, and total. The addition words, the order does not matter. The subtraction words are difference of, minus, subtracted from, less than, decreased by, less. And the subtraction words need to be interpreted because order does matter. So depending on the phrase, the order is either one way or another. Multiplication words are product, times, multiply, twice, of. Multiplication words, like addition words, the order does not matter. Division words are quotient, divide, into, ratio. Division, like subtraction, needs to be interpreted. The order does mean a specific thing based off of the words. So some examples. We want to write as an algebraic expression, and we want to let x represent the unknown number. So 5 decreased by a number, the order is going to matter. If we are taking 5 and we are decreasing it by a number, we are subtracting from that number. So 5 minus x. X minus 5 would not be correct because that would be a number decreased by 5. Two different things. Part B, the quotient of a number and 12. This is a division word. With division, order matters. The quotient of a number and 12 is a number divided by 12. So x divided by 12, or we could write it as the fraction x over 12. More examples. The sum of 4 and twice y. Well, the sum of means we're adding two things together. The first thing is 4. The second thing is twice y. What is twice y? That means 2 times y. So the sum of 4 and 2 times y would be 4 plus 2y. The sum of 4 and twice y. B. X less than the product of y and z. Now, this isn't the inequality x less than the product of y and z. We're saying x less than this, like 3 less than 5, or 17 less than 23. We're starting with the product of y and z, and then we're taking x less than that. So we are subtracting x. We are subtracting x from the product of y and z, y times z. So y times z minus x. More examples. 3 times the difference of a number and 10. Difference is a subtraction word, order matters. And when we say the difference of, it's like saying the sum of. The first thing is a number, the second thing is 10. The difference of a number and 10 would be x minus 10. We want 3 times that difference. So the x minus 10 would have to be in parentheses to multiply the entire 3 by it. B, 1/4 subtracted from 3 times a number. Again, subtraction, order matters. Subtracting from 3 times a number means we're starting with 3 times a number, 3x. And we are subtracting from that 1/4. 3x minus 1/4. Notice the x minus 1/4 is not in parentheses. We're not doing 3 times the difference of a number and 1/4. We're doing 3 times the number and then subtracting 1/4. The 3 has nothing to do with the 1/4. Okay, that's it. Fractions. we imagined we had this square split into, even if it doesn't look like it because of my drawing, 9 equal pieces. And we shaded 1, 2 of these pieces. This shaded part represents the fraction 2/9. Why does it represent 2/9? It's because there in the whole are 9 equal pieces, and the part of the whole that we're interested in has 2 pieces. So in a fraction, the top number represents the part, the bottom number represents the whole. We call the top number the numerator. We call the bottom number the denominator. So fractions are numerator over denominator. To simplify fractions, we often use a factoring process to reduce. What I mean by factoring is we can take a number like 15 and represent it as a multiplication problem. 15 is 3 times 5. So 3 and 5 would be factors of 15. What we're going to do is we're going to factor numbers until all of their factors are prime numbers. Prime numbers means that its only factors are itself and 1. The only multiplication problem you can come up with to factor the number is itself times 1. We can do this by creating a factor tree to do prime factorization, and I'm going to show you how those work. If we were factoring the number 40 down to a product of primes, we would come up with some 2 numbers that multiply to get 40. 5 is a prime number. The only thing that we can get multiplication-wise to give us 5 is 5 times 1. But we can factor 8 further as 4 times 2. 2 is prime. 4 can be factored further to 2 times 2. Now, the thing about prime factorization is no matter what choices you make along the way, you're going to come up with the same answer. Here we got that 40 is 2 times 2 times 2 times 5. But what if instead of 8 times 5, we chose 4 times 10? It doesn't make a difference. 4 can be split up into 2 times 2, which are both prime. 10 can be split up into 2 times 5, which are both prime. And once again, 2 times 2 times 2 times 5 is the answer we come up with once it's down to prime numbers. So the easiest way to reduce a fraction in terms of not making mistakes is to get the prime factorization of the numerator, the prime factorization of the denominator, and then cancel like factors on the top and the bottom. What do I mean by canceling? Well, if we have a fraction written in factored form, and we have a times c over b times c, we can see that there's a factor of c in both. We can cancel the factor of c on the top with the factor of c on the bottom, and it reduces the fraction to a over b. Let's look at reducing 36 over 200. We would have to get the prime factorization of 36. That can be 6 times 6 or 12 times 3. You're going to end up with the same answer if you use 12 times 3. 6 is 2 times 3, which are both prime. 6 is 2 times 3, which are both prime. We get that 36 equals 2 times 2 times 3 times 3. We do the same for 200. You could use 4 times 50, or you can use 100 times 2. 2 is prime. 100 is 50 times 2. 2 is prime. 50 is 25 times 2. 2 is prime. 25 is 5 times 5, which are both prime. We get that 200 is 2 times 2 times 2 times 5 times 5. So 36 over 200 is 2 times 2 times 3 times 3 over 2 times 2 times 2 times 5 times 5. We just made the replacements. We have a factor of 2 on the top that can cancel with 1 on the bottom. We have another factor of 2 on the top that can cancel with 1 on the bottom. Nothing else can cancel. We're left with 3 times 3 over 2 times 5 times 5, which is 9 over 2 times 5 is 10 times 5 is 50. So the reduced fraction is 9/50. And there are some other methods you could use, but it all comes down to the fact that these are the prime factorizations. How else could we get to 9/50 here? Well, we can just notice that 36 and 200 have a factor of 2 in common. 36 is 2 times 18. 200 is 2 times 100. We can cancel the 2's. We have 18 over 100. We can notice again both of those have a factor of 2 in common. 18 is 2 times 9. 100 is 2 times 50. And when we cancel the 2's, there's our 9/50. So you can write it that way. Or you can just divide top and bottom by the same number. 36 divided by 2 is 18. 200 divided by 2 is 100. 18 divided by 2 is 9. 100 divided by 2 is 50. Does it have to be 2? No. Just like when you're doing prime factorizations, you can pick any 2 numbers. Maybe you notice that both of these are divisible by 4. 36 divided by 4 is 9. 200 divided by 4 is 50. We know we're done when we hit 9/50ths because 9 and 50 have no factors in common. Or if you wanted to write that canceling style, 36 is 4 times 9. 200 is 4 times 50. Canceling the 4 on the top and the bottom is like dividing top and bottom both by 4. So lots of different ways we can think about reducing. Let's reduce some fractions. 42 over 49. 42 is 6 times 7. 49 is 7 times 7. I did that because I noticed that 7 was a factor of both 42 and of 49. I can come up with a multiplication problem involving 7 for both. And it reduces to 6/7. If you did the prime factorizations, 49 would be 7 times 7, both are prime. 42 would be 2 times 3 times 7. You can see the 7 cancels either way. If you did prime factorization, when you were done, you would remultiply the 2 and the 3 together to get the 6. Prime factorizations make sure you don't miss any of the factors, whereas coming up with 6 times 7 and 7 times 7 is more of a noticing process, noticing that 42 and 49 both have that factor of 7 to be able to cancel it. (11 over 27). While 11 is a prime number, its only factors are 1 times 11. And 11 is not a factor of 27, so this is already reduced. This is a prime situation. If you did factor trees, 11 would be 11 times 1, so just 11. 27 would be 3 times 3 times 3. You'd write out 11 over 3 times 3 times 3. Nothing cancels. So 11/27 is the reduced form. (88 over 20). I noticed that they're both even. We like that because that means we can go 2 times. 88 is 2 times 44. 20 is 2 times 10. Those 2's cancel. 44 over 10, they're both even again. 2 times 22. 2 times 5. And 22 and 5 have no factors in common. So 22/5. You could have also just divided them both by 4 if you noticed that. 88 divided by 4 gives us 22. 20 divided by 4 gives us 5. (63 over 72). Feel free to pause and try this one if you want. I'm going to go ahead and do prime factorizations just to get a little bit more practice with that. 63 is 9 times 7. 9 is 3 times 3. 7 is prime. 3s are prime. 63 equals 3 times 3 times 7. $72. That's 36 times 2. 2 is prime. 36 is 6 times 6. Each of the 6's is 2 times 3, which are prime numbers. So 72 is 2 times 2 times 2 times 3 times 3. I can cancel a pair of 3's. I can cancel another pair of 3's. I get 7 over 2 times 2 times 2, which is 7 over 2 times 2 is 4 times 2 is 8. Very sorry about that. Got that back all on the screen. I have to remember to check my monitors. Another way you could have done that, noticing that they're both multiples of 9. You can do a multiplication problem with 9 in it. 9 times 7 over 9 times 8. The 9's cancel, leaving us with 7/8. What about 64/12? Well, they're both even. 64 is 2 times 32. 12 is 2 times 6. 2's cancel. 32 and 6, both even. 32 is 2 times 16. 6 is 2 times 3. The 2's cancel. 16 and 3 have nothing else in common. So 16/3 is our reduced fraction. Multiplying fractions. It's very straightforward. If we have one fraction a over b, another fraction c over d, we multiply straight across the top and straight across the bottom. AC over BD, A times C over B times D. An easy example, we have 1/2 times 3/4, 1 times 3 on the top, 2 times 4 on the bottom. 1/2 times 3/4 would be 3/8. Now this one has a big multiplication in it, 15 times 13. But there is a way for us to simplify this before we do the multiplication. We can cancel any number on the top with any number on the bottom. Think of it this way. If we were to multiply, we'd have 2 times 5 over 15 times 13. And we see this 5 on the top. We can rewrite the 15 as 5 times 3. And then a 5 on the top cancels with the 5 on the bottom, giving us 2 over 3 times 13, which is a lot nicer, giving us 2/39. 2 and 39 have nothing in common factor-wise, so that is our reduced fraction. Instead of relying on us opening it up and rewriting it, we can use a process called, no surprise, canceling, when we notice the 5 on the top and the 15 on the bottom share a common factor. We ask ourselves, what is that common factor? It's 5. So let's go ahead and divide both of these by 5. 5 divided by 5 is 1. 15 divided by 5 is 3. That changes this to 2/3 times 1/13. 2 times 1 is 2. 3 times 13 is 39. As long as we cancel completely, our answer won't need to be reduced. 2/39 is already reduced as far as it can go. Feel free to try this one if you want. Now, you could multiply straight across the top and straight across the bottom. That's how we multiply fractions after all. You'd get 21 over 72, but then that would have to be reduced. Or you could use the canceling process. You can take care of all the reducing up front. 3 and 9, a number from the top and a number from the bottom, share a common factor of 3. So let's divide them both by 3. 3 divided by 3 is 1. 9 divided by 3 is 3. That changes this to 1/8 times 7/3. 1 times 7 is 7. 8 times 3 is 24. 7 and 24 share no factors, so it is in reduced form.